Hi everyone, this is a tutorial on MATLAB and it will be the first of a series of tutorials that will be available. This first tutorial is looking at an introduction to the software, looking at its platform as well as basic operations. This is a great way to get a crash course on the program or be a refresher for those of you who may have used it previously but are just returning to it after some time. So to begin with, what we have here in front of us is the MATLAB window setup. And yours can be set up in various ways depending on how you would like to view it. In my case, there are various forms of the way that you can have this set up, but there are definitely some standard elements. So the first one here is this command window. This is where we're going to be inputting all our basic information, typing in our operations, and being able to really almost run it like a scientific calculator by doing the operations in this section. Here on this workspace, this will show you all of the variables that we create, as well as the answer variable that will appear for every single operation. And then additionally, here is the current folder. So you'll notice that in my case, it has this standard path that it follows to where my MATLAB folder is. This is going to be the case for everyone. It will go to the standard MATLAB folder within your computer where you can save different files. We'll get into a little bit more about this ability to switch the current folder and why you would want to do that. Here at the top, you'll notice is your toolbar. We'll begin to use different elements of this as we go through the different tutorials, but it's good to become familiar with the various options. You may be able to move around these pieces. As you can see, you can move the command window around. You can change the way the workspace appears, depending on how you would like to move and view each of these. So, once we have a blank page, we're going to start off and start looking at some of the basic elements. One of the commands that I prefer to use is called format compact. Now to understand how this works, let's first look at just a basic value. So let's start off by looking at the platform and beginning to use some of its operations. So as I mentioned, MATLAB is very much like a scientific calculator on steroids. It has a lot more abilities than a basic scientific calculator, but it does all of the similar operations. And so we can do things such as addition. So 4 plus 4. You click enter. You'll notice that it creates a variable called ants, which appears in your workspace and will have the value of that operation. Similarly, we can do subtraction, we could do multiplication, and we use division with this forward slash. And so in these cases, you'll notice that every time we hit return, the ants variable gets relabeled. So initially it was 8, then became 0, 16, and then lastly 1. Ants is the default variable for any type of answer for a basic operation that is shown. Now you'll notice that very quickly in the command window you can use up the space. And although we will be able to have the ability to scroll, as you can see, it has the ability to scroll. Sometimes it is more useful to be able to have more information on a single page to view it. So for this reason, one function that I like to use is called format compact. What you'll notice in this case, and if we do 4 plus 4 again, is that the spacing between the operation, the answer variable, and the result all come in the form of 3 lines together versus having almost this double-spaced setting. So this definitely can be more handy if you're trying to get more information onto a single command window for viewing. Now, as you can see, you can do all of the basic functions. And one thing to keep in mind is that it does follow the standard mathematical procedure of PEMDAS, meaning that if we had something of the form 4 squared plus 2 minus 3 over 2 times it by 4, it's going to follow the operations just as you would in terms of potentially, and let's add in some parentheses somewhere, we'll put it, we can do this one actually, where it would do parentheses first, then your exponent, then the multiplication and division, and then any addition of subtraction. okay? So that would mean that it follows that same procedure. You'll notice that this answer would be different than if we remove those parentheses, right? So keep that in mind, that you want to make sure that you have your parentheses and any types of mathematical operations in the correct order as you would like it to be read, because it will read it as it does any other form. So if we had this and we added in the parentheses as we initially had it, you'll notice that this has a difference of 2. So keep that in mind. MATLAB is going to read it just like it would any other mathematical formula. So the next step is, now that we know that it can do all the basic equations, and you'll notice here for an exponent we use the almost like a caret type of symbol. That way we can say 4 squared, 4 to the third power. We're going to be able to use these variables and these operations to try something a little bit more complex. So first thing I want to do is I want to clear this window because I want to give us a clean space to work on. Now there's 2 ways to do this. The first one is where we type CLC. CLC, as you notice, will clear everything that was in the command window but does not replace or remove anything on the workspace. Our last ANS still remains. However, if we type clear all, it will eliminate anything that was in that workspace. So if you are in the case where you want to save what is in your workspace but want to clear out your window, then only use cell C. Generally speaking, you will always want to do a clear all before you do any types of operations, just to make sure that there's no variables in your workspace that may be interacting with your equations or with your procedures that you're doing in your current problem. So starting off, we notice that we can create a variable right off the bat by doing any operation. It creates the default ANS variable. However, we also can create our own variables, such that, for example, we would like this 4 plus 4 to be equal to a variable a. What you do is you do a equal and then do the mathematical operation. When I hit return, it appears and it shows a equals 8. It will also now appear in the workspace. Now, in some cases, you may not necessarily want to show every single time in the command window what that operation is. So example, let's create a variable b, and let's just say this is 1 plus 2, but we don't necessarily want to see b equals 3 in the command window. If you add the semicolon shown here, hit enter, you'll notice that it does not appear here in the command window, but it does get added to the workspace. So this is a handy way to be able to create a variable without having the hindrance of using too much of your command window space. So from here, you'll notice that you'll be able to create your variable names. Now you want to be careful with your variable names, because if you create one, and let's just say you have a number of variables with the letter b, and you have, say you want to create 2b equals 4. This is actually going to create an error, and it says an unexpected MATLAB expression. The reason being is that you cannot put a number at the start of a variable name. You can do b2 equals 4, and you'll see that came out fine, but you cannot start it with a variable. Additionally, you cannot do symbols such as @ or $, as you'll see that it also creates an error. There's different than when you start with a number. When you start with a symbol, it says the expression to the left of the equal sign is not a valid target for an assignment. In general, symbols such as the @ $, any of the typical ones you would find above your number, the number keys on your keyboard will not work. One way that you can introduce a little variability is by putting an underscore and then, for example, type in another addition to that variable. So this is a way that you can elongate your variable name while still making it readable. So in this case, I put b underscore alt equals 4, and that created with no problem. So keep that in mind. When you create these variables, you want to make sure that it is starting with a letter, does not include any symbols, and does not start with any numbers. Okay. So This gives you an idea of how we can create variables that are equal to a single value or even equal to a single operation. But we want to look at ways that we can create a series of numbers. And this is where MATLAB really has its strength, the ability to create what we call vectors and matrices. So a vector, and let me clear out all our variables here. A vector is a series of values that are found either in a column or in a row. In this case, I'm going to show first how to create a row vector. So you'll notice that I start off with a variable, a equals, and I have this open square bracket. The open square bracket, then you can input your numbers for your vector. In this case, I'm going to do 1, 2, 3, 4, close bracket, and I'm just going to hit enter. That way we can see how this appears. So here on the workspace, it will show as 1, 2, 3, 4, versus in the command window, it will show no brackets and no commas of any sort in this numbering. This is a vector of values that we considered a row. You can also create this saying 1, 2, 3, 4, and you get the same result. Okay, so those are two ways that you can create a vector, either using a comma or a space to separate each entry. You can also make this a column. In doing so, you will do the same process. However, you need to use a semicolon to represent the end of each row. And so in this case, I put a semicolon after 1, 2, and 3, and not after 4 because that is the last value. So in this case, you see that's the separation. When creating a column vector such as this, in this form, you must have the semicolon to represent the creation of a new row. There is a way to be able to do a column vector using this notation by the inclusion of one additional symbol. So if we have 1, 2, 3, 4, and that, if we hit enter, it would appear as a row vector. But if I put a single apostrophe, it will transpose this row vector into a column vector. And so this single apostrophe is comparable to the transpose operation you find in matrix operations or vector operations. You'll notice here on the workspace, the C and D variables show that they are column vectors by the use of the semicolon separating each of the numbers. So this is a great way to create some very quick and easy, useful vectors that you can bring into some of your operations. Now keep in mind that matrix operations or vector operations are going to work the same as they would in your regular math calculations. What this means is that you can add two vectors together, so a plus b. In this case, it becomes a new row vector, and I didn't label it anything special, and so it went to the default variable of ants. And so all it did was it added a plus b, which is 1 plus 1, 2 plus 2, 3 plus 3, 4 plus 4. So each corresponding entry was added together, just like you would in a typical vector math. Similarly, you can do subtraction, and in this case, you get a row vector of all zeros. It will also follow the occurrence of multiplication. So in this case, you'll notice the inner matrix dimensions must agree. In this case, this gives you a very definitive way of knowing why your operation did not work. And that's because, if you remember, inner dimensions for matrix or vector operations must be the same. So here comes the question. How do you determine what are the dimensions of your vector? Well, there's a handy function called size. Size, if you type in A, and if you'll notice right before I typed it in, and see if I can prompt it again, there was a little pop-up. And if you see this, size of x dim, this is actually a nice way that MATLAB helps and tries to provide you guidance. If I press on the more help button, a pop-up screen will show how this variable or how this function works. And so size tells you the array dimensions, and it gives you the syntax, meaning how it can be written out in various forms. You'll notice that you can assign the size to a single variable. You can have it assigned to two different variables, and we'll see how this works. But there's descriptions as well as examples. So these examples are truly useful in being able to capture a lot of the information you may have in terms of your problem and trying to figure out, well, how do I get this piece of information very quickly and to the point. And so, I highly recommend that if you ever do get into the position of having some issues with figuring out what function to use or how it works, definitely use the help function. In addition to it appearing here, you can also click on this question mark button here, and it will pop up a window. Let me bring this into view. It'll pop up this window in which you can search the documentation. This is very much similar to what you will find if you Google a function and say MATLAB size on the Google search toolbar. The website that you usually will get from MATLAB is comparable to what you will find here in this help section. So going back to our original issue, which was trying to figure out the size of this vector. If we type size of A, you'll notice that the answer comes out with two values. The first number will tell you the number of rows, and the second number will tell you the number of columns. As you'll notice, the vector A is a single row, and then each column here has 1, 2, 3, 4. So this has 4 columns. As we might have seen when I clicked on the help, you can break this apart such that you can have this say row column is equal to size of A. In this case, it would give me a variable row that's equal to 1 and a column equal to 4. And this might be a handy way for you to initially do this such that you remember the ordering. In the way that we designate our information for any vector or matrix, we do it in the row column format. And we'll talk about that more as we move ahead. But as we can see, we have that size A is 1, 4. If we do size of B, it is also 1, 4. So you'll notice that the inner matrix dimensions, 4 and 1, do not agree. So for us to be able to multiply vector A times this by vector V, we would actually need to change vector B such that it would have 4 rows and maybe 1 column. And we know how to do that. We can set B prime. So if we say size of B prime, this now has 4, 1. Now if you remember, this single apostrophe is the transpose, such that B times that single apostrophe would create that vector in a column format. So as a result, A times B single apostrophe would actually give us a value of 30. So this follows the basic format. So let's clear this out and let's talk about a little bit more of some of the operations we may want to do. Now, as I mentioned, the columns and rows have a very definitive way of being labeled in these vectors. So for example, we have A, which is a vector of 1, 2, 3, 4. Say, for example, we want to change or actually modify what this first value is to a 0. We can do that quite easily. What we can do is we say vector A, and we want entry 1, 1. This refers to the row position and the column position. Here, we set that equal to 0. If we click on A again, you'll notice that now that first entry has changed to a 0 from its previous 1 value. Similarly, that's a good way to be able to call for a number. Say, for example, you need to know what is the entry in the first row, 4th column of vector A. That tells you that it's the number 4. So this type of labeling is useful in not only assigning values, but also recalling values. So considering this, let's now look at some matrix creations. So a matrix is basically a series of vectors put together. So if we create a matrix E, we can have it equal 1, 2, 3, 4. That's the first row. The semicolon at the end designates that this is going to be the end of that first row. 5, 6, 7, 8. And you'll notice what I've done is I've created a matrix that has 2 rows and 4 columns. If I take the size of E, it should show 2, 4, representing the row-column sizing. The matrix again follows the same type of abilities to recall and assign values using the row-column designation. So if we want to change, and let's say 2, 3, so if this was second row, third column, so this should change entry 7. If we would like to change that, say, to a value of 9, we can do that. And you'll notice that when I enter, it will show E, and it will show the new value in place where we located it. Similarly, we can also figure out and recall a value. Now you'll notice that there was an error, right? When I did E3, 2, it said index exceeds matrix dimensions. Well, in this case, this is row 3, but this only has 2 rows. So because it has no existing third row, it will give you some error such as this. So whenever you see this, this possibly means that you put in a value that does not exist here. So let's change this and say 1, 4. In this case, it will recall the value in the first row, 4th column, which is the number 4. Again, these matrices are going to follow the same operations that you would have for vectors in terms of addition, subtraction, multiplication, and division. With this in mind, let's take our matrix E, and let's just say we want to multiply all of these values by a value of 2. What you can do is do a scalar multiplication such that 2 times E will multiply every single entry in matrix E by a value of 2. Okay, so 2, 10, 4, 12, all of these are double the original value. Now say for example, we didn't want to actually multiply the entire matrix by this, but only a single row. We can do that quite easily. So here we have E, and we want to multiply this first row. So what we will do is we will say E, first row, all columns. So in this case, you'll see that this colon designates all columns when it's represented by itself. We can say is equal to 2 times E, 1, all columns. So we're basically replacing that first row with twice its value. And so you'll notice that in this case, every single value in the first row only were multiplied by 2. Second row was left alone. Now let's just say in the second row, we only want to change the first 2 values. So second row, but only first column and second column. So second row, but we only want column 1 and 2. We can do that using this colon. Here, when I put a number before and after the colon, it will act as a kind of limit guide, telling me from column 1 to column 2. In doing this, I can then say 2 times E, row 2, 1, 2. I want that to equal twice the original value. And so you'll see 10 and 12, which are twice the respective values. Similarly, you can use this colon operation in the row variable as well. So in this case, we could do all rows of the third column. We multiply this by a half. In this case, you'll notice that we have 210, 412. Here we have the 3 and 4.5, which has now divided these two values by half. And the last two are by themselves. You'll notice that in this case, the values now show slightly differently than they did originally. This includes a series of zeros after these whole numbers because of the third column in which we have this 4.5. There's ways that you can change this and format it. We're not going to get into too much detail about that, but if you're looking into more information, you would want to look into discussions for format long and format short. So I think these are the key operations that we want to show in terms of multiplying and by a scalar for a matrix. Now, you can also do this such that you can divide your variables. It's recommended that you use fractions for the multiplication. So for example, you can do 0.5 times this by e to divide each of the terms by half. One more item I would like to show you before I complete this video is the use of some standard functions that may help you create matrices. So the first one is called zeros. So if we create a matrix, and zeros will create, as you can see here, has different ways of creating this. It can create a vector or a matrix of a specific size. If I just put 2, it will create a 2 by 2 matrix of zeros. I can also do zeros of 1, 3, meaning 1 row, 3 columns of all zeros. So depending on how you label it, it will determine the size of the vector or matrix being used. But in both cases, it will produce a matrix or vector full of zeros. There's similar function called ones, such that you can create a matrix of all ones, or you can even create a vector of all ones, depending on what your desire is. So with this, I'm going to conclude this first video in reminding us of what we've covered in here. We've looked at the basic platform layout, some of the basic procedures that follow the standard PEMDAS operations. We looked at creating vectors and matrices, as well as labeling those cells and reassigning the different entries, and knowing the vector operations, vector and matrix operations that are doable with each of these components. So I encourage you to practice this, look at different examples that you may have in your own applications, and test this out before moving on to tutorial 2.